In this video, we are constructing proofs algebraically. Let's get straight into the first example. It says, prove that the sum of three consecutive positive integers is always 3 times the middle number. Now let's remember the word integer, that means whole number. So we need to show that the sum of 3 consecutive whole numbers, positive whole numbers, always ends up being 3 times the middle number. Now, I'm going to show you the wrong way of trying to prove this that a lot of students try and do. What they do is they pick 3 consecutive numbers. They might go for 7, 8, and 9. Then what they would do is work out the sum of those 3 numbers. And they would find the answer is 24. Then they would say, yes, look, 24 is 3 times the middle number, which is 8. So they've done that and they think they've proved it. They've shown that the sum of 3 consecutive positive integers, 7 plus 8 plus 9 in this case, happens to be 3 times the middle number. However, this is not a proof. All the student has done in this case is show that it works for this set of 3 numbers, but we're being asked to prove that it works for any 3 consecutive numbers. So just because it works for 7, 8 and 9, it doesn't mean it works for 10, 11 and 12, or 8, 9 and 10, or 100, 101 and 102, for example. Now, a student could try all of those and find that the sum of those numbers always does happen to be 3 times the middle number, but that's still not a proof that it works in every single case. You can never try all the possible sets of 3 consecutive numbers. So we need to find a smarter way, and that's what we're going to look at in the rest of this video. So here's what we do. We introduce algebra. We're going to start by saying let n be a positive integer. The beauty of this is that n can represent any number, so we're not just proving it for one particular set of 3 consecutive numbers, as you'll see. By the way, this is a pretty common starting point for lots of the algebraic proofs, as you will see in this video. So we've said n is a positive integer. The next key step is to work out what 3 consecutive positive integers would be. And here's where a lot of students also go wrong. They decide they're going to use 3 different letters of the alphabet for 3 consecutive integers, but that makes life very difficult. What you can spot is that if n is a positive integer, then the next number along is just going to be n plus 1, and the one after that will be n plus 2. So those 3 numbers, n, n plus 1, and n plus 2, are going to be consecutive. Let's just check this makes sense. If n was 7, let's say, n plus 1 would be 7 plus 1, that would be 8, and n plus 2 would be 7 plus 2, and that would be 9. So we would have 7, 8, and 9, and those are indeed consecutive positive integers. But remember, this works for any value of n, so these could represent any 3 consecutive positive integers. Next, let's work out the sum, because that's what we're trying to prove has a certain property. The sum of those 3 is going to be n plus 1 plus n plus 2. That's those 3 values simply added together. And if we add those, we can get a simplified expression, which is 3n plus 3. We've got an n plus an n plus an n plus a 1 plus a 2 if we collect the like terms, and we get 3n plus 3. Now, what is this? This is meant to be 3 times the middle number. The middle number of the 3 consecutive integers was n plus 1. And 3 lots of n plus 1 does work out as 3n plus 3. So that's great. We can show that really clearly by saying that is 3 lots of n plus 1. All we're doing is factorising from here to here. So we've factorised it, and this is now obviously 3 times the middle number. So we've proved it. The sum is 3 times n plus 1, that's the middle number, and that's what the question asked for. In this example, we need to prove that the square of an odd number is always 1 greater than a multiple of 4. We're going to start this in a similar way. We're going to say let n be an integer. Now, the problem is we don't just want to deal with any old integer, we want to be looking at odd numbers. And the way to do that is to consider 2n plus 1. If you think about it, if n is an integer, a whole number, then 2 lots of n is going to be an even number because that's in the 2 times table. And then if you take an even number and add 1, you've got an odd number. So 2n plus 1 can be used to represent any odd number. We need to show that the square of any odd number is always 1 greater than a multiple of 4. So let's square this odd number. 2n plus 1 all squared is simply 2n plus 1 times itself. So that's 2n plus 1 times 2n plus 1. Now you should be comfortable expanding brackets. If you're not, check out lesson A4D. Multiplying this out is going to give us 4n squared plus 4n plus 1. And now what we want to do is show that this is 1 more than a multiple of 4. And in this case, what we can do is see that we have got a multiple of 4 here, and then we're adding 1 onto it. And we can make that really clear. We can factorize just part of this expression, so not the whole thing, because if we factorize the whole thing, we'll just go back to this form. But what I'm going to do is factorize just this bit. And that's going to give me 4 lots of n squared plus n. And then we've still got the plus 1 on the end. Notice I haven't fully factorized. I could have also taken an n out, but all I'm trying to do here is show that 4 goes into this expression here. So this whole thing is a multiple of 4. And then what we've got is a multiple of 4 with 1 added on. So that's why the square of an odd number is something in the 4 times table plus 1. In this example, we need to prove that the product of any 2 odd numbers is odd. Now, in this case, students often make the mistake of doing something like this. Can you see where this is going wrong? The student has started off with something sensible. They've gone with let n be an integer. They've found an expression for any odd integer. And then what they've done is they have multiplied the odd integer by what they think is another odd integer. But all they're actually doing in this case is multiplying that odd number by itself. So just like in example B, they are going to deal with the square of an odd number. And if they carried on with this proof, all they would do is show that the product of an odd number and itself, i.e. an odd number squared, is odd. And that's not the same as proving that the product of any 2 odd numbers is odd. So in this case, we need algebraic expressions for any 2 odd numbers. Here's how we do it. In this case, I start off with 2 letters representing integers, m and n. That means they could be completely unrelated. And now we can have 2 completely unrelated odd numbers. So 2m plus 1 can represent an odd number, and 2n plus 1 can represent a different odd number. It could also represent the same one if we want, but the point is they don't have to be the same. Whereas in the wrong example, if you used 2n plus 1 and 2n plus 1 again, you are only proving a statement involving an odd number multiplied by itself. What we need to do is prove that the product of these is going to be odd. Remember, product means what you get when you multiply them together. So we have got product, which is going to be 2m plus 1 times 2n plus 1. Again, this is a skill you should have from lesson A4D on multiplying out brackets. This ends up giving you 2m times 2n, which is 4mn. Then you have 2m times 1, which is just 2m. And then you have positive 1 times 2n, which is 2n. And then you have positive 1 times positive 1, which is 1. And this expression can't be simplified, so we've got 4mn plus 2m plus 2n plus 1. Now, to show that something is odd, this product is odd, what we need to do is show that it is kind of like these. It is 2 times an integer plus 1. And we're going to do that by factorising a 2 out of all of these and then leaving the plus 1 on the end. So just this section of it can be factorised as follows. I'm taking a 2 out here, and then I've got 2mn plus m plus n in the brackets, and then we've got the plus 1 on the end. And what this does is show me that I've got the product is 2 lots of something plus 1. And everything in this bracket involves multiplying and adding whole numbers together. So that is a whole number. So we've got 2 times a whole number. That means this bit is even. And then we add 1, and that means it's odd. So we've just shown that the product has a form like this. It's 2 times something plus 1. Here's example D. Pause the video and have a go at this one for yourself. Here's a proof. So we're dealing with any 2 even numbers. So we've started off with m and n as integers. Then even numbers are going to have the form 2m and 2n. Remember, m could be any integer, but if we double it, we end up with an even number. So these can be used to represent any 2 even numbers. The difference is what we get when we subtract. So 2m subtract 2n is going to be this. We can simply factorise out the 2. And I want to do that because I want to show that the difference is even. And I've now shown that it's 2 times some other expression, and that's just m minus n. That's the difference between 2 integers, which is going to be another integer. So 2 times an integer is obviously going to be even. Here's question E. Pause the video and have a go at this one for yourself. Here's a proof. In this case, we've started by saying let n be an integer. We can then use that n to generate 3 consecutive integers, n, n plus 1, and n plus 2. They want us to prove something involving the product of the first and the third, and the square of the second. So let's do the product of the first and the third. The first number is n, the third number is n plus 2. The product is what we get when we multiply those. So n times n plus 2. Multiplying that out, we get n squared plus 2n. The square of the second number, so that's the middle number, n plus 1, all squared, which then gives us this, which multiplies out to give us n squared plus 2n plus 1. And hopefully you can see that the product of the first and the third is basically the same as this, but it doesn't have the plus 1 on the end. So this is 1 less than this. The product of the first and the third is clearly 1 less than the square of the second. That would be an acceptable proof.